I hope the screen is visible, and I welcome you to the week 6 live session of live discussion sessions of quantum chemistry of atoms and molecules. Today, mainly, we are going to discuss the assignment 4 solutions, problems and solutions, and it was about the harmonic oscillator. Sorry, not harmonic oscillator, but the rigid rotor problems. And then we will solve some numerical problems which were left in the last class. I have shared the questions earlier. I hope you had the time to check those problems, maybe else we will solve it anyway today. So to start with, let us discuss a little bit about the rigid rotor problems. What are the equation we might be using? First of all, let me write it here. Rigid rotor. So actually, why to study the rigid rotor as a quantum mechanical system is important? Because we know that when we will deal with diatomic molecules like uh, oxygen, even not homoatomic, even heteroatomic like HCl or suppose HBr, these kind of molecules, then the rotation along the bonds become important. So they are also rotating. Last time in the harmonic oscillator problem, we relate the harmonic oscillator problem with the stretching and bending, those vibrational motions of that diatomic molecules. Now we are going to discuss how the rotational energy is getting impacted. So that rotational, so that actually can be studied by solving the Schrodinger equation for a rigid rotor problem. So in a rigid rotor problem, usually there are two masses, like one, suppose for here we are discussing one small, one capital mass MA, and one small mass capital MB, and suppose the distance is L, the internuclear distance, or in usual our terms r0, and if they are the distance between center of mass, so the center of mass is supposed to be near the uh, atom which have the higher mass, right? So the center of mass will be something around here. If my MA is greater than MB, by looking at this also we can understand. So this is my center of mass. Sorry for that. Let us come back. So this is my center of mass. Suppose the distance from here and here is something like r1, and this distance is r1 and this distance is r2. Then actually we can also define it. I mean, suppose this was a two body problem, right? But this discussion related to this two body problem will have much higher difficulties because there are too many variables. So what we want to do is that we convert it to a one body problem, suppose like this. So where our center is like this, and we consider a reduced mass. So that reduced mass is mu, and the radius of gyration is now r. So we'll consider it somehow that, so this is the center, and this is our reduced mass. So reduced mass we earlier discussed, right? Reduce, what is a reduced mass? For a vibrational case also we discuss what is reduced mass. Mu is nothing but, for this case, ma mb divided by ma plus mb. So this is reduced mass. So we can convert a two body problem to one body problem, and from here also what we understand is that the Schrodinger equation is, and the one more change will be there, as now we are mainly going to deal with the rotational motion. Now the instead of first of all, this r is going to be constant because we are discussing a rigid rotor, right? So that is one point, that is of that we the assumption is that the bond length is not going to change. So the bond length is not going to change. That is the one main assumption, and that is why this is called as rigid rotor. Now, for this the Schrodinger equation will be a little different, because the Hamiltonian we are going to take, the Hamiltonian generally we take in the Cartesian coordinate in terms of x, y, or z. So mainly we discuss with 1D problems we are discussing earlier, right? Harmonic oscillator in case of harmonic oscillator, or 1D box problem. But now, as we are going to deal with the angles mainly, the rotational angles, now theta becomes important. So that's why we will move to a different coordinate that is mainly known as polar coordinate. So I will define the polar coordinate first a little bit. So what is polar coordinate? So for polar coordinate, we will start from the Cartesian coordinate. We will discuss what is the relationship between the Cartesian coordinate and the polar coordinates. So generally, if we consider this our Cartesian coordinates, so z is along this, y along this, and x along this. And suppose our our reduced mass, or suppose any vector, the position of that is along here. So suppose this is x, y, z, right, as a three-dimensional coordinate. Now in terms of how can we go from a x, y, z to a r, theta, phi, that is a polar coordinate, how can we convert it? So first of all, the vector, so the line, so position along joining the origin and our reduced mass, or some particle, so that is, suppose that distance, or that is r. Okay, so that is r, and that is making an angle theta with the z axis, z axis or z axis. So that is making an angle theta with z axis. So if we can consider it like that, then we will see that uh, that that z is, so what is cos theta? Cos theta is uh, your
Excuse me.
yes.
Why it is required that we have to transform from Cartesian coordinates to polar coordinates? What
So
is the reason there?
right now, now we are not. So we have fixed our bond length. So we will not discuss. We will not see the change along the r. But we, as a rotational motion, we are going to check that how this. So this was moving. So this bond. So we are going to discuss that how this two-body problem is going to move in the space. So that rotation along. So it will have a rotation. So MB has a different kind of rotation. MA is going to have a different kind of rotation. So that pathway is different. But when we are going to discuss a one body problem, so that time, what, first of all, from a two body problem we constitute a one body problem, and we define mu, that is the reduced mass. And now, while discussing how this reduced mass is going to rotate at the space, so now our angle theta becomes important. How the rotational angles. Now we are going to deal with the rotational angle, and that is why this discussion in the polar coordinate will be better, because in Cartesian coordinate we will not be able to, mainly we will not be able to um, uh, so it is based. So I will give you a another I will give you right now the discussion I am going to give you, that we are going to deal with the rotational angle, and that is why r theta phi is important to work with r theta phi. But very soon we are going to deal with hydrogen bond atom. I guess you have already studied from the lecture, right? And there you have already seen that there is a similarity between this rigid rotor and a harmonic, so this hydrogen atom, in terms of that they both use the spherical harmonics. And that case, you are going to see in the Hamiltonian, the potential energy have a term of 1 by uh, so the potential energy will have a term of 1 by what I remember, x y z, x plus y plus z, something like this, and that we cannot separate easily. And but when we discuss it when we will change it to the polar coordinate, that separation will be easier. See, right now we are not dealing with a one-dimensional problem but a three-dimensional problem. That is why the separating of variables would be very important while solving the Schrodinger equation. So, to best to give you answer is that if we use the polar coordinate, then we can do that easily. So that is the main point what I'm trying to highlight. That is why we need to go to polar coordinate instead of Cartesian coordinate. Are you answered?
Yes, it
Okay.
is quite
Okay.
satisfactory. So
Okay.
much of information in your lecture.
Okay.
Thank you.
Another thing, if you will see that in hydrogen bond, what I was telling that in the potential energy, so that is V is equal to, I don't remember the exact term. That is, I guess, 1 by R is going to come. So, but 1 by R, you know what is R. So, so actually, let me define this first, and then I will go to that part once more. So let us get the relationship between x, y, z to r, theta, and phi. So here you can see what is cos. So if you see the cos theta is z by r, base by hypotenuse, right? So so this is along the theta. So it is making an angle theta with z. So we can say that z is equals to r cos theta. That is one of the important relationship we obtain. Now see what is the relationship between r theta phi with x and y. So to understand that, we need to project this vector means this vector, the one I am highlighting right now. Let me, maybe I can color that in a different color. So this is our vector. Now what I want is to project it onto the xy plane. So how we can do that, and what would be the length of that? So suppose this is my projection of that vector uh, on the xy plane. Okay, and that projection is actually what will be the length of that. So that would be, if you see, so this angle was theta, and this angle is 90 minus theta, right? So now our cos 90 minus theta, right, is how much? That is your base. So that uh, we don't know yet. So that I will write it uh, base by hypotenuse. Hypotenuse is r. So this is the base. What I was saying, this projection. This is base, right? Right, and this is my hypotenuse. So that, and cos 90 minus theta is sine theta. So base by r. So the base is r sine theta. First of all, the g is r cos theta, and now we know that the modulus or the magnitude of this projection vector is along the xy is r sine theta, right? Now this r sine theta, this projection operator, I'll remove this base, right? So because I will show you another angle, maybe with a different color of ink, suppose green. So this projection operator now making an angle, suppose phi, with the x-axis. Okay, now what would be, now we will get some relationship between this projection operator and the x, right? So what are the relationship we are going to get, and I will write them in the green color, maybe that will be easier. So now if you see, so now this is making an angle phi with x-axis. So now my cos phi, right, cos phi will be again the this base, right, this uh, I'll remove this second overwriting, maybe I will use this. divided by, now my base is the hypotenuse, right? So that is uh, cos is cos phi is x by r sine theta. Please let me know if there is any doubt. So now the relationship becomes between x is equals to r sine theta cos phi, right? Similarly, now suppose there is making phi with x, then it will make an angle 90 degree minus phi with y. So that is also cos, but cos 90 minus phi, right, will be y by r sine theta. Now cos 90 minus phi is sine phi. So that is why my y will be equals to r sine theta sine phi. So I will just rewrite my relationships here. So what we got between the polar coordinate and x coordinate, that is z is r cos theta, x is, now see there is a symmetrical thing between this, is x is r sine theta cos phi, y is r sine theta sine phi. So z is only dealing with the main vector, so that is why it is r cos theta, but x and y both are dealing with the projection operator, right? Projection of r onto the xy plane. So that is why we are dealing with r sine theta in both the case. So that is constant, r sine theta and r sine theta. Now for x it is r sine theta cos phi, and for y it is r sine theta sine phi. So sorry, I made a mistake here. So this should be sine phi. Okay, and in terms of another thing, I can write it that x square r can be written as x square plus y square plus z square. So I was waiting for this term, because what I was saying earlier, that you have already, I think, gone through the lectures of Professor Datta regarding this week 6 or week 7, that hydrogen atom problem that we are going to discuss on the next week. But the important thing was that in the Hamiltonian, in the potential energy, there was a 1 by r term, 1 by r in potential, right? So if you think in terms of Cartesian coordinate, then you're in denominator you are going to get root over x square plus y square by z square. So which will be very hard to separate each x, y and z, but it will be very easy to deal with only 1 by r, right? That is why in these spherical harmonic problems, spherical harmonic means these rotational problems, it will be very easy to deal with the polar coordinate rather than the Cartesian coordinate. Okay, so now these are the relationship are important in polar coordinates, and mainly from here, I think next it was discussed that how the what was the Hamiltonian. First of all, the Hamiltonian will be something like Hamiltonian, and mainly for spherical harmonics, the Hamiltonian looks like this. D by dr plus 1 by r square sine theta d by, so d by d theta sine theta d by d theta, and then one more part is 1 by r square sine square theta d2 I should write del here. Del phi square. So when the we can separate out the variables. So here, what are my variables? Here my variables are r, theta, phi. So then we can directly use d instead of del. Del is partial derivative and d is the derivative, right? So when we can separate all the terms, then we can write it d. But in case of rigid rotor, we don't require this part. Why? Because we are not going to so my already we have defined it is a rigid rotor, so r is a constant, so d by dr or del by dr is going to be 0, so we will not require this, but we will require this rest of the part. So can you please confirm if I have written this correctly, this 1 by r square sine theta d by d theta sine theta d by d theta, or did I made any mistake in writing? It was a big expression. I am not looking at any notes. I may make some mistake. Can you please confirm? So I will rewrite it here. Please let me know if I am making any mistake. So 1 by r square sine theta d by d theta sine theta. Here I should write del because r and theta both are there, so we could not separate it out yet. And in case of here, 1 by r square sine square theta del phi square. I'll just look at my notes if I have written it correctly.
Yes, it is correct.
It is correct, right? Means 1 by r square sine theta d by d theta sine theta d by d theta, right? So I can proceed from here, I guess. Yes. Okay. So now there is a relationship between, now as we are only going to deal with the angular this rotational motion, so we have to invoke instead of this linear momentum, we have to work with total angular momentum. Total angular momentum is this. So right now I am discussing what are the important uh, relationship or the expression or equation that are going to required for the solution of these assignment problems and next whatever numerical problems we are going to solve. So total angular momentum is defined as this operator L, capital L. So that is actually, if you think of like this, so what we know about the relationship between the kinetic energy operator and the kinetic energy operator and uh, uh, our linear momentum operator, that uh, our energy is kinetic energy is something like p square by 2m, right? So that is in case of linear case, linear when we are discuss about linear momentum or linear motions. I should better write it like this, and I can write instead of uh, so I will write kinetic energy, kinetic energy. But when we are discussing this rigid rotor problem, there at that time we can also see it terms of this total energy, that is Hamiltonian operator, that can be discussed in terms of this. Instead of p square, now we have this total angular momentum, and that divided by not 2m but 2I, where I is moment of inertia. So that is actually equals to mu r square. So this mu is this mu, that reduced mass, and r is the radius of gyration. So that is my, so mu r square is my moment of inertia. So I can also get a expression for my total angular momentum from the Hamiltonian, as you can see. So L square by 2I. So what would be my uh, so if I write it, so it is L square by 2 mu r square, right? And I think I have missed one part. So this is not actually my Hamiltonian, so that I have made one mistake. This is actually my Laplacian, del square. Okay, so and my Hamiltonian is actually, I'll write it here, I don't have space. So that was actually minus h cut square by 2 mu, right, del square, right? So this is my Hamiltonian. So my Hamiltonian is actually, if I have to write it in terms of Hamiltonian, so where should I write? I will use the next page maybe. So what I was discussing, our this del operator, del Laplacian operator, sorry, that is del square. So that is 1 by r square d by dr, r square, not r square, right? We are not dealing with r, we are only going to deal with the theta and phi part. So that is 1 by r square sine theta d by d theta sine theta d theta, d theta, plus 1 by r square sine square theta d2 by d phi square. And again I should write it in del term. Now my Hamiltonian will be, what I was saying is, minus h cut square by 2 mu del square. So this term will come in front of this r square sine square theta, r square sine theta d by d theta sine theta d by d theta, plus 1 by r square sine square theta d2 d phi square. So that is my Hamiltonian, and we have already established that Hamiltonian is our total angular momentum, square of that divided by 2 into moment of inertia. So what I can write it, or if I break it down, that is 2 mu r square. So what I can write, I will get an expression from total angular momentum also, right? And that is, I will remove this, right? So what I am going to get is, if I am multiplying this, so I am going to get h cut square, 2 mu r square is gone, 1 by sine theta d by d theta sine theta d by d theta, plus 1 by sine square theta d2 by d phi square. So this is my expression for total angular momentum. So in these lectures, actually in week 4 lectures, Professor Datta has discussed something about the some parts about the angular momentums, right? And how they commute with each other, the components. So L square actually you can uh, write like Lx square, right? You should not forget to write the hat Ly square or Lg square. Now, what we have learned so far is that this L square will commute only with one of the components, and this is not with only Lz but also with L square Lx. So one of the assignment problems I saw is there was a, I guess there is some mistake in the answer. So individually these components are going to commute with your total square of the total angular momentum. So they commute. So when they commute, they have a common set of eigenfunctions, right? What Sir has already proved. And as they have a common set of eigenfunctions, so they can be simultaneously measured. So what I mean by that, so there won't be any uncertainty. So that Heisenberg uncertainty principle will come when they don't commute or they don't have a common set of eigenfunction. Now, as they are commuting, so they have a common set of eigenfunctions, and because of that, we can simultaneously eh, measure L square as well as the Lz. But what we won't be able to measure is that we cannot measure Lx and Ly simultaneously because they don't commute. Similarly, Ly, Lz, they don't commute. Because of that, we won't be Lz, Lx, we won't be able to measure that simultaneously. What they are equals to? So they are, if you do it, we will get this is equals to Ia. So there is a symmetrical thing about that. So means you don't have to remember this, but as you are means if you do it, if you write it many a times, it will you will see there is a pattern. So LZ now next is Ly like that. So I am not remembering this. So suppose Lx Ly, how you will remember this? So there is nothing, but there is a pattern between this. So by that you can remember these things. I'm not sure if I am mistaken the minus sign. I don't think there is a minus sign, but if there is, please check on the notes. But that's how there is a pattern. What I'm trying to say, they don't commute, and hence they won't be. We can't be measure them simultaneously. And what else? And what else we have to remember is that the wave function of this rigid rotor is something like the spherical harmonics, right? So these are the two main so M modulus and the L is there. So M is in superscript capital M and L is in subscript capital L, and Y is known as spherical harmonic, that is actually your uh, theta part, capital theta. So that depends on both L and M, both quantum numbers, and multiplied by your capital phi, that is going to only depend on this M or this magnetic quantum number, and L is ultimately you are going to in the in the hydrogen atom problem you will see that is known as azimuthal quantum number. So I am giving you these names because I think you have already gone through the lectures about the hydrogen bond, hydrogen atom, right? So, so this is a so there is a theta dependent part and there is a phi dependent part. So you have already seen from the lecture this phi dependent part is nothing but uh, uh, this is can be written as a constant, normalization constant, and multiplied by, it could be either plus or minus I capital M phi, right? And this normalization constant is mostly 1 by root over 2 pi, I guess, and M is a magnetic quantum number which can be 0, plus minus 1, plus minus 2, and go on, but there is a certain limit to it. So the limit is actually up to plus minus L. So that you will see that I think Professor Datta has already discussed how there is a limit to this magnetic quantum number, and this theta part, which I'm not going to discuss right now, but this theta part is actually going to have a solution like solution in polynomial that contains, and suppose there is going to be a normalization constant overall, right? What I was discussing, NML, and so there is something like this PML cos theta. So this is known as a associated Legendre polynomial. So associated. So earlier, in case of harmonic oscillator, we were introduced to harmonic polynomial, right? And now in case of the spherical harmonics, we are going to have another kind of polynomial in the solution of this Schrodinger equation, that is associated Legendre polynomials, and obviously that e to the power plus minus, or suppose let us go with the I m phi. So that part is from the phi dependent part, and this left hand side part is from the theta dependent part. So this is my overall suppose, so this is not only my theta but also my phi m is also there. That is my overall spherical harmonics. So that is my wave function is going to looks like. So and your, so we know that your modulus of m is going to be less than equals to your L. Okay, so that is another. So there is a limit to your magnetic quantum number. So we are just touching it point by point, not detailed like what Sarah has gone through, because we have to solve numerical problems, right? So with this background, let us go to solve the assignment 4 problems. So assignment 4 questions. So first I'll prefer if you give me the answer instead of so if you give me the answer directly. Huh? So the first question is the correct relationship connecting the Cartesian coordinate x and the spherical polar coordinates r theta phi is where x can be equals to what? So this is the first point what we touched upon, that polar coordinates, right? So what do you think? What is going to be the answer?
R sin theta cos phi.
R sin theta cos phi. That means the B, right? So B is going to
P.
correct answer, right? Now for our means practice purpose, let us write the all the a, relationships here, so that we may require them in the upcoming slides. Right? And R is root over x square plus y square plus z square, and there are many other, like what would be the cos theta? Cos theta will be theta would be cos inverse z by r. Those things are already there, right? So something like, and one more very important thing what I missed out in the discussion about the polar coordinates, that is your r can go from 0 to r, right? That is the distance, but there is some limitation about the range of theta and phi. Theta can go from 0 pi, that is 180 degree, right? And your phi can move 0 to 2 pi. If you see like this, 0 to pi, and for phi it is 0 to 2 pi, you will see you are going to get the whole sphere. You may think that how theta will be 0 to pi, then let us go to that image here. So suppose theta can be 0 to pi. So 0 is along z axis, right? When this r is on the z axis, then my theta is 0. And when it is on the negative z axis, then it is 180 degree or pi. So theta can go from here to here, right? I hope you got my point. So theta can grow from 0 to 180 degree. Not the whole again come back 360 degree. Zero can go from theta can go from 0 to pi, as well as your phi. Now phi can go from 0. Phi is when the projection operator is on the top of the x-axis. Now it can go from phi can go from 0 to 2 pi. So it can come back here, right? So that is the one of the boundary condition when you are going to solve this phi dependent part. So where this exponential im phi term comes. So you will see that using these two condition you can build a sphere around this xyz. And another thing, your volume element d tau is going to be r square dr. Earlier in case of 3D three-dimensional problems, we were taking the volume element as d tau, which is dx multiplied by dy multiplied by dz. But for a polar coordinate, it will be r square dr sine theta d theta d phi. Let me So drawing of it could be a difficult. I guess Sir has already shown it in his lectures. X, Y, Z. So this volume element. Suppose this is the change that is going to take place. This is the volume element. So this is the volume element, and this is my distance r, which was making a theta angle, and now it is made an angle d theta with this. So, so this distance, so we are having a rectangular slice, something about a sphere. Huh? So we are going to now first look at the each of the length of this rectangle. So by looking at that, we will get this part is something like r d theta. Now this is r and this is dr, right? This distance is dr. Now what about this distance? So that is a projection around. If you think about that, that is a projection here. And so that is your r sine theta was here, and which was making an angle phi with this, right? When it is going to d phi here, so it is going to make an r sine theta d phi, sorry, d phi. So now what are the uh, for all these rectangular I should not say rectangle. Rectangle is in 2 dimension, so this is a rectangular box, right? So what are the length of or dimension of each of the box? One is dr, one is r d theta, and one is r sine theta d phi. So in overall we get r square dr sine theta d theta d phi. So that is our volume element. Okay, that is how we are defining our volume element. In case of d tau xyz coordinate, we directly write it like dx into dy into dz, right? But here, as the coordinate has changed, so our this volume element has also been changed. Okay. Now coming back to here, I will write it once more here, that for here our d tau is r square dr sine theta d theta d phi. Okay. Now the second question, that periodic boundary condition used for phi dependent part of Schrodinger equation of a rigid rotor builds upon the requirement of wave function to be. So if you remember, this builds upon this phi, capital phi plus 2 pi is going to be phi, right? So this is built upon this relationship, this condition, and that is the single value, right? That means that if you are moving from phi angle to pi, from a phi angle, you are going to come back at that same position. So that is going to be, you are going to have a single value. Obviously it is continuous, but the main thing is that your single value, and that is why we can equate these two, right? That, so this is the answer of the second question. Now question number 3, that phi dependent part of the rotational wave function is, so let me first write it on,
Excuse me.
yes.
If it is asked for theta dependent part,
uh,
then what is the answer?
if it is going to be a theta dependent, then it is also not imaginary. What I remember from the equation, it was something minus 1 to the power z, right? So there is no directly, it was not a imaginary thing, it was a real. It was, it was a mixture of things. If you remember, there are trigonometric equation, right? Cos square theta minus 1 to the power modulus of m by 2. Then, so mainly a trigonometric function, you can for now you can say that is a trigonometric function, and mostly a polynomial, because we have discussed it, right? It was an associated Legendre polynomial was there, right? So if it was a theta dependent part, then mostly you have to write a polynomial instead of any trigonometric function. You directly write on a polynomial. So that would be correct enough. Okay. So the phi
Okay.
dependent part is mostly a into e to the power plus minus I m phi. So as you understand, this is an imaginary as well as an exponential function. So these two. So when there are square shaped options are there, please remember these are multiple correct answers are there. Okay. Now question number 4. The polynomial function in the rotational wave function. So that is what we are discussing just now. So the polynomial function in the rotational wave function bear the name of Legendre. So this associated Legendre polynomial we are discussing. So this is in the rotational part, that is the theta dependent part. Now question number 5. The energy E and degeneracy of G of J equals to 2 rotational levels with the rotational constant B is what? First of all, uh, so so as I told you that for as why we are studying this rigid rotor problem, because it is a very standard system. When we solve this rigid rotor system, we can get an idea regarding the rotational energies of a system, right? Obviously we are going to get some quantized energy, and that energy can be related to the rotational energy of a diatomic or a multi-atomic molecule, but that for a later case. But now let us think about a diatomic molecule. So so if we have a rotational energy or these rotational transitions, then what is the most important or fundamental thing we can get for a diatomic molecule? Can you answer me? So we know that rotational energy is something in joules. It is um, h square. I'm not sure if I am writing the exact thing. Let me take help from you. 4 pi square I see, or 8 pi square I, if I write it like that, and j into j plus 1, that is I think in joules. And for spectroscopy part, it is 8 pi square IC. I hope I am not making any mistake. This is in centimeter inverse. How did we get that? Earlier for numerical problems we were doing it, right, previous day, that we divided E by HC. So your joule divided by HC, you will see you are going to get something in terms of meter inverse or centimeter inverse. So if you take the value of C as the speed of light, that is 3 into 10 to the power 8, 10 to the power 10 centimeter per second inverse or centimeter second inverse, then you are going to get the centimeter inverse. Anyway, this constant, this is a constant for, this is constant for one molecule, because you understand that I have constant for a particular, for a molecule. Not all the molecules are going to have the same thing. So that is known as B. That is rotational constant. That is a constant for individual molecule. Why? This I has mu r square. So this mu, so if you know the molecule, then you know the reduced mass. If you know the reduced mass and you know the energy or the rotational constant, then you are going to get this bond length. So that is the importance behind studying or solving the rigid rotor problem. By doing this, we are going to get the idea about the rotational, not the rotational but the bond length. So from the rotational spectroscopy, we can get the bond length. One more thing, what Sarah has already discussed about the rotational energies and individually he means what is the gap is going to be, right? So it is, so here J is rotational constant. Sorry, J is rotational quantum number. Rotational constant is B. This is rotation, you can say as rotational quantum number, or you can state as different rotational levels, right? And it will start from 0, 1, 2, 3, like that. Okay. So, and then what would be the energies of each state? Energy is what we have already defined, that energy Ej is B into J into J plus 1. So like that, if we think about J equals to 2, then the energy will be B into 2 into 3. So that is 6B, right? So it could be either second option or the third option. But we also have to see that J equals to 2. Okay. So this J is nothing but this, what I was discussing earlier as L. Okay. Here. The total angular momentum. Actually, this J is total angular momentum, that is L plus M kind of thing you have to understand. So if J is, if J has a limit, if J is 2, then what I told you, that M could be, there is a limit, right? So J is 0, plus minus 1, plus minus 2. So how many degenerate states you are going to get? Can you tell me? For J equals to
5.
2, how many states are there?
5.
5. Now they are degenerate when there is no perturbation. You get my point? When there will be some perturbation, then these states are going to have different energies. Like 0 will be, 0 will have some energy. Now plus minus 1 will have different energy. It will suppose, so that is very important. So just wait, I switch on the plug of my computer charging. So that, some water. Very thirsty. So what I was telling that for j equals to 2, when there is no perturbation, then the degeneracy is 5. So actually let us first complete this answer. This for question number 5 we are going to get E 6b and g is the degeneracy is going to be 5. But when there would be some perturbation, then these 5 states which are like this, suppose 5 states, they are going to have differences in energy. That is what I was saying. Okay, it would be 1, it would be plus 2, minus 1, minus 2, like this. When there is perturbation, and when there is no perturbation, then they are going to be degenerate. So what kind of perturbation? So if you think now, so rigid rotor is an ideal system, right? But now, do you think that rigid rotor is a means is possible in normal case? It's not, right? The bond length is going to fluctuate. What we have discussed in the vibrational spectroscopy, right? So, for our assumption was that the vibrational that amplitude will be very less for a rotational motion, but in reality it's not. No bonds are rigid, right? So when the you are going to discuss with the means non-rigid rotor, that will actually account for an perturbation. So and that time this degeneracy is going to be lifted, but that is for a another uh, course you may say, because you can go through the lectures of molecular spectroscopy by Professor Datta, that is now available on YouTube. The course is molecular spectroscopy. I guess that course is again going to be offered on the next semester. You can take that course also. Anyway, um, so what we understand from here that first of all the energy of a rotational state is going to be B into J into J plus 1, and what is going to be the energy difference, the delta Ej, that is B into J plus 1. Suppose the gap between J plus 1 to J, so J plus 2 minus B into J plus 1, it is going to be 2B into J plus 1. If you take J plus 1 as common, then your B is there, J plus 1 as common, then you are going to J plus 2 minus J, that is 2. So 2B into J plus 1, that is the energy gap. And you are going to see actually, so these transitions are is going to be something like that, that 2B, 4B, 6B, 8B, 10B. Okay. So now for a rigid rotor, what you are going to see is that your transitions in a, so these are spectra actually. Okay. So your spectral lines are going to be equispaced. What do you mean by equispaced? See, the gap is 2B in all the case. So if you can record your spectra, suppose you know your molecule, huh? Suppose you know it is HCl. So first of all, let me tell you, for a homo diatomic molecule like oxygen, nitrogen, these kind of molecules you won't be able to get the spectra. First of all, because their dipole moment is 0. So you are only going to deal with the heteroatomic and heterodiatomic molecules like HCl, HBr, this kind of molecule. So for that kind of molecules, when you are going to record a spectra, you are going to see that the rotational spectra are actually equispaced. So you know you have HCl, so you know what is your mu, right? know mu. Okay, so you can get what is B, right? Because you know Planck constant, you know 8 pi square, C you know, right? The only unknown is you don't, so you are getting 2B from the spectra. So you have recorded the spectra, so you got the spacing between two lines, that is 2B, right? And you know that all the things inside here instead, so I is mu r square. So suppose you don't know the bond length and you know all the things, then you will be able to determine the bond length. So that is the importance of this rotational spectroscopy or this rigid rotor problem. Okay, now we have digressed it too much. So let us come back to the question number 6. I hope the discussion we had was means you got some idea from there what we were discussing. So now let us come back to question number 6. So this question deals with the polar plots. So I think lecture number 4 of week 4 has discussed about the polar plots. So there we have to find which statement is correct. So the first statement is the range of the angles is 0 to 360 degree for theta as well as phi. This is not correct, right? Theta is 0 to 2 pi and phi is 0 to 2, 0 to pi and phi is 0 to 2 pi. So the first option is incorrect, right? First statement is incorrect. What about the second statement? That value of the plotted function of angle is represented by the distance from the origin. This is actually correct. What about question statement 3? That sine of the function is shown by plotting the opposite side of the curve. That is actually not correct, right? Because the sine can be shown using a different color, right? Sine cannot, means you are not, you are eventually going to plot, but you don't know that that is negative or not. So that depends. So you, so for here, polar plots, your theta is going to be like depend on the theta, you have some magnitude or some amplitude of your wave function, and that you are going to plot. So actually statement 3 is also incorrect, because not by plotting opposite side of the curve, but giving a proper color to that. Now what about statement D? That a circle is obtained when a function is constant with respect to phi. Actually this would have been theta and phi. One would be theta and phi. With respect to theta and phi is the independent variable. What do you think about question statement D? A circle is obtained when the function is constant with respect to theta and phi is the independent variable. Is it a correct statement? It is not a correct statement, because you are going to get a hemicircle.
In case of phi,
Yes,
yes,
you are going to get a hemicircle when the
yes,
function is
hemisphere.
constant, right? Because in case of polar plot, when we are discussing only about the theta, so theta can be only going from 0 to pi, 0 to 180 degree. So half of the plot is going to be unused. So that's why you are going to get a circle. Okay. So only right answer is this B. That is the value of the plotted function of an angle is represented by the distance from the origin. Okay. Now let us come to question number 7, that is your angular momentum along the z axis, that is LZ. So it is a multiple correct answer. What do you think it is going to be? So for LZ, so what I prefer is this determinant from this I, J, K first of all, and then this X, Y, Z, then Px, Py, Pz. So this is your L actually. So this is going to give you here I, J, K are the unit vectors. So when you are choosing I, then you are going to have Y, Pz minus Z, Py. Then when you have Z, then you have actually you are going to take a minus instead of plus because you are going to take xpz minus zpx plus k. So let us take this as plus and this minus and this is plus, and when it is k vector then it is xpy minus ypx. Now you know what are, so this is your Lx, this is your Ly, and this is your Lz, right? So from here we can see Lz is xpy minus ypx, right? We know what py is. Py is h cross by I d by dy. What is px? Px is h cut by I d by dx. So we'll just put them. So h cross by I will get common. So x into d by dy, my actually del by del y is better, right? Then y del by del x. See, first option is correct. Is there any correct answer other than A? So this is what actually we have
D,
discussed in Cartesian
D is also
coordinate.
correct.
Yes. So D is also
Option D
going to
is
be
also.
correct because that is going to get you, you are going to get it from the polar coordinates. So actually there are two options correct. One is A and another is D. Now let us go to the question number 8. So the properties that can be determined simultaneously. So what are the properties that can be determined simultaneously? Those operators which commute, right? So if A and B are two operators which commutes, that means AB minus BA is 0, then you are going to have a common set of when the operators commute, they have common set of wave functions or eigenfunctions. I should write eigenfunctions. Hence, they can be determined simultaneously. Here you will see that this commutator is 0, this is 0, this is 0. They don't commute. Actually, your A, B and C, all three should be the correct answer. Okay. So your total angular momentum, actually L square, commute with each of the component Lx, Ly and Lz, not only with Lz. So SAR has shown only with Lz, but it can commute also with Lx and Ly. So actually you are going to determine these properties simultaneously, A, B and C. Now question number 9, motions involving the change in the phi would require to be taken in the consideration. So it is said that where d by d phi is going to be important, d by d phi. So you know Lg is minus IH d by d phi, right? So in case of the angular momentum operator along the z axis, will consider the motion involving the change in the phi and also the total square of total angular momentum, right? Because if you remember the this discussion, so it was something has d square by d phi square, right? Something like that term is there. So A and D both will consider the motion involving the change in the phi. So uh, up to this portion, do you have any question? I think this was the last question of the assignment 4. So do you have any queries till now or doubts?
No. Okay. ठीक.
If not, then let me ask you one question. So we have, so that is from harmonic oscillator, huh? So just a tricky question. So for harmonic oscillator, simple harmonic oscillator, SHO, we know the total energy is V into, my total energy of a state is V plus half into H cross omega, right? And we know the potential energy is half m omega square x square, right? Or half kx square, right? This we know. So if we know the total energy and potential energy, will we be able to calculate the kinetic energy also? Is my question clear? So we have a energy expression for a vibrational state, right? That is EV is equal to V plus half multiplied by H cross omega. And from the starting onwards, we know the potential energy is half kx square or half m omega square x square. Okay. So from here, what I wanted to know, obviously there is a so you need to know the Hamiltonian, right, for harmonic oscillator. So that is what was the Hamiltonian for a harmonic oscillator? It was a tough one if you remember, right? So we can take it by two methods. One was that using ladder operators, and another was that uh, by that algebraic method. So no, the algebraic method was the uh, ladder operator, and another was something like that you are breaking down that uh, what was that some power term we are breaking down, right? So where the Hermite polynomial thing was introduced, analytical methods, right? Anyway, so just think about this. This is a homework problem that for a harmonic oscillator, we know the total energy of a state. We can calculate, determine that. We know the potential energy, but the kinetic energy is never discussed. Why so? So the answer is there in this slide only. Okay. So just uh, have a look at that. That why kinetic energy is not discussed, even when the expression for total energy and the kinetic energy is known. Okay. Just a homework. Just give you the thought why the kinetic energy is not cannot be determined, or if it is determined, why it is not discussed. Arupji, is my question clear?
Actually, due to weak network, I am getting your voice only. Video is not coming because
Oh,
of my.
my video is not coming. Okay, okay, okay. Let me check once. Let me check once if it is.
You know, this is my problem.
Oh, okay,
My
okay, okay,
network is not stable now.
okay, okay. So actually, you will get the question in the notes maybe when you will see the note. So what actually I was asking that for a harmonic oscillator, we have the expression you know, right? That the expression for a state is v plus half into h cross omega. So that can that we can determine. And one more thing we can know that is the potential energy term, right? That is half k x square or half m omega square x square. But the kinetic energy term is not discussed. Why so? So that is my question. And that question, that answer is something related to the commutatorship. Okay? Just give me the thought and we'll discuss it on maybe on the next day. For now, let us solve these numerical problems what were left yesterday. Or let me put in a way that what we did not discuss, could not discuss due to the time permission in the previous day. So, Arupji, if you can't see this solution, how we will do that? Uh, um, anyway, let us.
Now, now it is okay. Now it is
Okay,
okay.
okay, great, great. So now let me reiterate the question. Is
Uh,
3.29? This is from a yes. So actually
no
this
problem right now. Okay.
okay. Are you you are not getting you are not hearing properly, right?
No, no, now it is okay. It is
Okay,
fine.
okay, okay. So this question is from Macquarie Simon's book, Physical Chemistry. So the question actually deals with that generally we have solved the particle in a box for a problem and we have defined that the box have walls, infinite walls at position 0 and say A. Okay. So the question, so in this question what they are asking is that get the wave function if the potential walls are at minus A and A. Instead of 0, it is at minus A and A. Is this part of the question is clear? That is question number 1. That get the wave functions. And the wave functions will look like this. Means prove the wave function will looks like this when the walls are at minus A to A. Then, so this is the first question. The second question they are asking, that what about the energy expression of this kind of particle in a box problem when the walls are at minus a to a, what is going to be the energy expression? Is it going to be similar when the walls are at 0 and 2a? So is it going to be same or different, right? So this is actually the main question. So there are many things written, that's why I tried to gist the question. There are mainly two questions that prove that the wave functions expression of the wave function looks like this when the walls are at minus a to a, and get us the energy value, huh? So let us do this. So the Schrodinger equation is something like minus h cut square by 2m d2 psi by dx square plus, obviously the potential energy is 0, is equals to E psi for a particle in a box. Inside the box the potential is 0, so the Schrodinger equation looks like this, right? So this is not changed, right? When we use the bound, so actually by changing the position of the walls, what we are doing is that we are changing the boundary conditions, not the Schrodinger equation, right? The Schrodinger equation is same as before. So let us see how the Schrodinger equation is. So d2 psi by dx square is minus 2me by h cut square psi, right? And let us assume that minus 2me, sorry, let us say plus 2me by h cut square is k square, okay? So the equation becomes minus k square psi, right? And obviously if I bring that to this side, is plus k square psi is equals to 0. So this is an differential equation, right? So the trial solution will be same as before, that your psi nx is going to be a cos x plus b sin x. Up to this part there should not be any change, right? So this is the trial solution of this Schrodinger equation. But now my boundaries are changed, right? So according to the boundary conditions, obviously at boundary my wave function is going to be 0, right? Because of two things. One is the continuity, right? So my psi n at minus a position is going to be equal to the psi n position at, so I should not write psi n now, right? Because I have not introduced the quantum number. So let us write only psi x and psi minus a minus s. So this is going to be 0, right? So this is my boundary condition. So what is that? So psi of minus a is psi a cos k. Actually this is minus a, right? Please let me know wherever there is a doubt. Thus b sine minus k, and that is equals to a cos ka. See, this for cos function, cos minus ka is cos ka, so that we can write. But instead, in case of sine, this minus will come out, so it will become b sine ka. Okay, so this is for, so this is equals to 0. So let me write as equation 1. And what about psi at a? So that is a cos ka plus b sin ka equals to 0. Up to this part, do you have any question?
No, okay.
Okay. Now let us add 1 plus 2. Now equation 1 and equation 2. The b sin ka, that part is going to vanish. So we will deal with a cos ka equals to 0. Okay. And when we take a subtract 2 from equation 1, we are going to left with b sin ka equals to 0. Okay, we are going to get these two equations from equation 1 and 2. Now see, there we don't know if what is the value of a, what are the value of ka. A means capital A and B, and what are the values of angle we don't know. So we cannot, right now we cannot say anything about the values of capital A and capital B. Okay, so there is a general solution for this equation 3 and equation 4. Suppose I am writing this as equation 3 and this is equation 4. So the general solution would be that your k is going to be n pi by 2a. I know this is very arbitrary what I am writing right now. I will discuss each and every step. Okay. So the general solution for both the equation will be k is equal to n pi by 2a. Why so? See, if you put the value in the first equation, not the first but this equation 3, then you see your equation looks like, I will just write it in a different color maybe, then it will help. Suppose, so see a cos, now I am taking a value of k here, so it would be n pi by 2. Okay, where obviously here n is 1 2 3, obviously it cannot be 0, right? If it would similar to the 1D box problem, for a general solution what we have done, if it would have been 0, then it would have been 0 all along the box, which is a trivial solution, so we don't want that. So now what we are discussing, that n pi by 2 is 0. See, when a can be 0, when a can be 0, a can be 0 when cos n pi by 2 is not 0, right? It has some value. And when that is true, when n is even, n is even, then a is 0. I'll prove it to you. See, when n is even means n is 2 4 6, then see your cos become cos pi, cos 2 pi, cos 4 pi, like this. Okay, so your that time that cos function is not 0, but the overall function has to be 0. So then your a will be 0. Okay, now let me take another color. In case of b, so it is b sine n pi by 2 is 0, if that is the solution. Now see, when n is odd, that is 1 2 1 3 5, then see this sine n pi by 2 is not 0. When sine will be 0? When sine will be 0? When the n is even, right? Sine pi, sine 2 pi, sine 4 pi, sine 3 pi. So these are the values when sine term becomes 0. But see, sine pi by 2, sine 3 pi by 2, sine 5 pi by 2, these are not 0. So if that term is not 0, this overall equation will be 0 when only b is 0, right? So we get two boundary conditions from here. Are you following? Or is there any doubt till now?
Yes.
Okay. So, so we get two things, that when n is even, then a is going to be 0. When n is odd, b is going to be 0. So let us write when n is, so let me use the another color. N is even, then a is 0, right? Then what my psi becomes? Psi n x, b sine n pi by 2 x, right? Will you agree?
Yes.
Okay. So when n is even, now when n is odd, then my b is 0, then my wave function will be a cos n pi x by 2. So depending on where we put our origin, or where do we put our um, where do we put our coordinates, the wave function actually mathematically have different expression, right? Because see, earlier when we used, so in lectures, in suppose in Professor Datta's lectures, we have taken a boundary 0 to a, right? That time what is the wave function we obtained? Is something like some normalization constant, which I will write it after, but sine function we got, right? Sine n pi x by sine n pi x by a, right?
Yeah.
But now you see, when we take a wave function, a boundary minus a to plus a, we are getting wave functions like this. So first of all, the question wanted that if we can get, oh, I have made one mistake, and let me correct it. N pi by 2a, right? So I missed the a's here. Very sorry for that. So I missed the n pi by 2 kx, right? So n pi by 2a is the k, and here also I missed this a. So So these we have already proved. And what is the value of the normalization constant? Let us see for any one of them, maybe both of them. So for a normalization constant, what we need to do? We need to get psi star n and psi n dx. Here your boundary is from minus a to plus a. I cannot take 0 to a. Here my boundaries are changed, right? Minus a to a. Let us see how what we are getting. So we are taking a green color. So let us do with the below one. It is a square, right? Minus a to plus a cos a square n pi x by 2a dx. So I will just multiply it by 2 and take 2 in the denominator outside the integration. Why I have done it? Because I know the expression for that cos 2 theta is cos square theta minus sin square theta. I always forget this, so I remember at least this. This is the way how I remember that 2 cos square theta could be cos 2 theta minus 1. I always forget this, so I try to remember from the scratch that cos 2 theta is cos square theta minus 2 minus sin square theta, like this. So right now my integration will become minus a to plus a. 2 cos square theta is cos 2 theta, so it will be cos 2n pi x by 2a, so it would be something like, so I can erase the 2 from here, right? Because 2 will cut this minus 1 dx. So it would be a square by 2. Now what is the integration of cos n pi x by a? It would be a by n pi into cos will become sin n pi x by a minus x integration of minus 1, and it will be plus a to minus a, right? So let us see, a square by 2 a by n pi. First it would be sin n pi, right? A cut minus a, then I have minus a, so it will be minus of a by n pi sin minus n pi. It doesn't really matter, you will see why. And it will be minus and minus okay. So sin n pi is 0, here also it is 0. What are the things we are left with? A square by 2 is minus a minus a minus 2a. So a square by 2 is into minus 2. Did I make any mistake here? Yes, I have made a mistake. See, it is cos 2 theta plus 1, right? 2 cos square theta. So I'll just take this. So it will be plus and it will be minus here. So overall it will be plus. I hope you got what change I just made. So I made a mistake here and I just changed it. So I am getting something as a square. So a square should be 1, right? So that my, or I should write 2a, right? So a square a square a should be 1 as a normalization constant. So a square is 1 by a. So a I am going to get is 1 by a to the power half. So this is my normalization constant. Okay. So when you will work with this b sin x part, you are also going to get same normalization constant. Okay, believe me for now. So ultimately, let me take a blank slide here also. So what we got is that psi nx is going to be a cos, sorry, not a, right now I can write the normalization constant cos n pi x by 2a when my n is odd and I can write it as a sine function when n is even. So this is proved. Okay. So what we have seen from now is that when we have changed the position of the coordinates, the wave function changed. But now what about the energy? So earlier here you see, look at this part, focus on here. I will just highlight this portion. So we'll use this expression for the energy. Obviously, we know what is K, right? From here, so we'll put the value of K from here. So let us see. So we know that 2ab by h cut square is K square, and we also know is that K is n pi by 2a. So we'll put it here, n square pi square by 4a square, right? So we'll get an expression of En, suppose energy of the nth state, as n square pi square divided by 4a square multiplied by h cut square divided by 2m. Okay, what is h cut square? H cut square is h square by 4 pi square. So I'll just erase this here. Please let me know if there is any concern. So I will cut pi square, right? What I am left with? N square h square divided by 32 m a square. Okay, this is the energy expression for the 1D box we are uh, taking care. Okay, now what about the energy expression when suppose What is the usual energy expression we get for our box when the it is given, suppose n square a square by 8 m a square, right? If, or suppose let me say L square. Now suppose my box length is 2a, what would be the energy expression? It would be n square a square by 8m 2a square. See, this is also nothing but n square a square by 32 m a square. So the interesting thing what we are seeing is that the if we change the coordinates, then the expression for wave function is changed, but expression for the wave function is changed, but the observables like energy, what we are discussing right now, real observables or physical observables, that expression is same, because when the box is from minus a to plus a, in that case your box length is 2a, but the coordinates are different. Now when your infinite walls are at 0 and 2a, in that case also your box length is 2a, but your coordinates are different, right? What I hope you are getting what I'm trying to say. In both the cases you are going to get to different wave functions. Expression, mathematical expression for the wave functions are different, but when you are solving for the energy expression or any other suppose physical observable, you will see that the expression for that or the value for that expression is going to same. So the wave function, let me write it here, expression of wave function will depend on the coordinates we place, but expression of the physical observable like energy expression what I just shown you, observable is going to be same irrespective of where we put the coordinates. Did you get my point? Or so
Yes,
this
yes,
was
yes,
actually
yes.
a very big problem. Means we tried to do it in a simple manner, but the main thing is sometimes you will see that in some books in Levine they take a different boundaries and they obtain a different wave function. That often lead to thinking like that. Why we are taking a so why at the first place we take the boundary condition from 0 to a instead of minus a to plus a, because 0 to a will make our life easier. That understanding was easier. Now as we are now much more confident about the Schrodinger equation, now we can play around with the coordinates and see what are the possibilities, right? So this is a very good problem in that sense that we can understand that there is means there is a mathematical expression is changed for the wave function, but the information it bears. So what we know that the wave function bears all the information, and we need to put appropriate
operators on it to extract the information. So when we will put the operator on, even though they are different expressions of wave function, they will lead to same values of energy or same values of physical observables. So that is what the take home message is from this numerical. Okay. Now actually we have three more questions, but I don't think so we should go ahead because I also have an invitation to attend. Sorry for that. So can I close the session today for today here, or means I need to attend something? So will it be okay with you if we can stop 10 minutes earlier? Maybe usually we have a session for 2 hours, but if we have a session 10 minutes less, I hope that is not a problem.
Yes, 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 no problem.
Okay, okay.
No
Thank you
problem.
very much. And then we'll meet on the next Tuesday, what is coming. And please look at this solution for these problems, maybe. And we will solve the hydrogen atom problem. And this problem also we will solve. Okay. So we'll try to make up for that 10 minutes on that Tuesday, and maybe we will go even longer because that hydrogen atom have many things to discuss. So we'll solve the assignment 5 on that day, and these numerical problems what are left out. So with that, we'll stop it today. I hope the session was useful and helpful, I guess, informative. So with that, today we'll close this session, and I thank you for attending. And
Thank you for a beautiful lecture.
my pleasure, my pleasure. So with that, let us stop it today, and we'll meet on the upcoming session. Thank you very much for joining.